Before moving on to our next application of dynamic programming, we're going to take a little bit of a diversion and talk about trees. Trees come up quite often in dynamic programs. We should be familiar with trees already. Trees are graphs that have nodes and edges, and they're particular graphs where there's no cycles. A cycle is any sequence of edges and nodes that we can find a path from our original starting node back to that node, much like the directed acyclic graph case. When we talk about trees this time, we're going to be focused on rooted trees. To think about a rooted tree, we take a particular node of that tree, called the root, and we think about hanging the tree off of this root, so that the root is at the top and then we get progressive levels down. The root is an arbitrary choice, and if we choose a different root, then the tree stays the same, although when we look at it in the rooted tree format, it can potentially look a little bit different. When talking about rooted trees, we gain a new set of dynamics. There's a sense that the tree moves from the top, the root, down progressively through the nodes. This gives rise to a lot of different structures. First, we'll focus on ancestors, predecessors, and descendants. We'll focus on a particular node in our tree, 4. First, the ancestors of the node 4 are all the nodes that are immediately following 4. In this case, all the ancestors of 4 are the nodes 5, 6, and 9. We denote the ancestors of a node by A, so this is the set A4. The predecessors of the node, of a particular node, is the node coming immediately before that node. Every node has exactly one predecessor. In this case, the node 4's predecessor is R. We denote the predecessor with P. So this is P4. The descendants of a node are the set of all nodes that follow 4, not just the ones that are immediately after. The descendants necessarily include the ancestors, but also include other things. In this case, the descendants of the node 4 are going to be circled in fuchsia. The descendants now include the nodes 5 through 9. We denote the descendants by D, so this set is D4. In addition to properties of particular nodes, ancestors, predecessors, and descendants, there's also more global sets of nodes. We're going to focus on leaves and depth. First, we'll talk about leaves. The leaves of a tree are all the endpoints, sort of the opposite of the root. In this case, the leaves of the tree are the nodes that we're circling in blue. We can characterize the leaves of the tree as all the nodes that have no ancestors. We denote this by L of T. These are the leaves of the tree T. The concept of depth also is going to rise in trees. The depth of a node is the distance that it takes to get from R to that node. For example, if it takes a path of length 2, that is, it takes 2 edges, then that node is at depth 2 from the root. The depth is sort of a parallel structure in this tree. Here we can circle all the nodes of depth 2 in fuchsia. These global properties of depths, leaves, and these local properties of ancestors, predecessors, and descendants are going to be important when we talk about dynamic programs that are structured around trees.